And I want to start by talking about integrated photonics and why do we care about it. When we think about photonics or optics, we usually think about bulk optics, right? We have beam sizes on the order of centimeters, and we use mirrors to route the light to the places where we want them to go. In contrast, integrated photonics actually can guide, confine, and modify the light in really tiny structures by using high refractive index structures. That makes it so that the beam sizes that we're dealing with are now on the order of micrometers or wavelengths. And that makes it so that routing that light just consists of bending the material that's confining. So compared to bulk optics, integrated photonics offers miniaturization, reconfigurability, in the sense that if we change the properties of the material, then we change the properties of the light itself, robustness to environmental fluctuation, alignments, low cost, and scalability, in the sense that we can fabricate a lot of these structures very close to each other with very high repeatability and very high yield. And while that's very advantageous, in reality, the commercial applications of integrated photonics has mainly been limited to communications applications on like sending data through an optical fiber, basically. And another field where integrated photonics has a lot of potential is in imaging. And here I'm just showing a typical architecture of an imaging system. We have a light source, then a series of lenses and other components to treat that illumination, then their sample, then another series of lenses to capture the light and treat it, and finally a camera to detect light. And if we look at this diagram, actually every single component of the imaging system has the potential to be.
Vale. Mi hermano está hablando toda la nos acabamos de otra semana. Mi hermana arriba y sois iguales. Está por ahí.
Yeah. Speakers off. Okay.
Así su nombre y también la universidad. Todo. Sí.
Technology.
Vale.
Keep going. If you look at the diagram of an imaging system, pretty much every component except the sample, of course, has potential for integration. And while that's true, there's actually not been a lot of work on integrated photonics for imaging applications, and that's where this thesis comes. And the end goal is to take all key specialized equipment, such as a microscope, to a tiny chip that has the same functionality, but it's much cheaper and much more compact. And in particular, I'll be focusing on CMOS photonics, which is a subset of silicon photonics. And silicon photonics is the branch of integrated photonics that uses silicon to confine the light. And CMOS photonics goes a bit beyond that and uses the exact same layers and the exact same fabrication processes that are made to realize integrated electronics. And these processes are called CMOS electronics or CMOS processes. So CMOS photonics are integrated photonics that use the exact same process. And that makes it, or that gives several advantages. The first one is low cost. These processes are really low cost at scale, about $1 per millimeter square of area. They offer monolithic integration with electronics. Since we're using the same processes and the same layers, we can fabricate transistors right next to photonic components, as I'm showing here in the diagram, and they're on an actual chip, and without having to do anything special. And we also have very high yield and very high scalability, very high fabrication control. And that's thanks to the fact that we're piggybacking on the 60 years of development of CMOS process for electronics. And as a result, actually, silicon photonics is probably the most mature fabrication platform for integrated photonics, so we're going to leverage. And so in particular, in this thesis, we explore novel sources, devices, and applications that enabled by CMOS photonics for imaging applications. And the rest of my talk is divided into 3 parts. In the first part, I'll talk about my work on integrating the light source and the detector on the same chip to realize single chip lensless holographic microscopy. And then I'll switch gears and talk about my work on the analysis of non-uniform OPA architectures for beamforming applications, and that's more focusing on the use of integrated photonics for processing of the illumination before getting into free state and interacting. And I'll finally conclude my talk and also go over some of the other work I've done during my thesis that I done that time. All right, so with this, I'm going to jump into the first section, which is, again, realizing single chip reflection lensless holography. And most of you will be familiar with the traditional optical most of you will be familiar with the schematic of a traditional optical microscope, where we basically just directly image the light that interacts with the sample in a camera. And I'm showing here a typical microscope image of an array of 20 micron beads, 20 microns. And optical microscopy, traditional optical microscopy, is simple in the sense that it doesn't require any computational treatment of the acquired image, but it has several limitations, including that it cannot image transparent objects and that it doesn't store any 3D information about the sample. And in contrast, holographic microscopy, instead of directly imaging the light that interacts with the sample, it images the interference between that light and a reference beam. And that results in the formation of a hologram in the image plane. And that's actually the hologram of the same sample up on top. And by looking at this, it's clear that one of the main disadvantages of holography is that it requires computational reconstruction to go from the acquired hologram back into the sample. But in return, what we get is that we can actually image transparent objects because holography is sensitive to the phase response of your sample. And it also allows for 3D reconstruction because information about the parallax of the system is stored in these interference fringes that you see on the image. And as a result, holography has quite a lot of applications, including topographic imaging, real-time process monitoring, gable-free biological imaging, because cells are usually transparent, so it's actually pretty hard to image them with a traditional microscope, and also 3D reconstruction. Nevertheless, current holographic microscopes are actually bulky, they're expensive, and they have a pretty strong field of view versus resolution trade-off because they require an objective, and if you want to have a high resolution, you need a higher magnification microscope, and therefore you lose field of view. And an alternative to the use of traditional holographic microscopy is what's called lensless holography, where we basically take a system, the traditional system of a holographic microscope, and compact it into this, which just has an illumination, a sample, and an imager. There's two main things that happen here. One is that we get rid of all the lenses on the system, and that actually eliminates the field of view versus resolution trade-off, because since we are not using any lens, and now we don't have that limitation in the field of view. And we're also, instead of using a separate reference beam path, what we're doing is using as reference path or as a reference light, the part of the light that, or the illumination that goes through the sample but doesn't interact. And that's great, and it makes a much simpler system. And basically all the requirements are on the source. So this source needs to be coherent, and here I'm just showing a diagram of a coherent source where you can see how there's a very nice constant spacing between the maximum and minimum of the wavefronts, and also there's perfect vertical lines, which means that spatially they are nice. So again, like coherent sources are both spatially and temporally coherent. Temporal coherence means that different parts or parts of the wave emitted at different times can interfere, and I'm showing here an example of a non-coherent, non-temporally coherent source where you can see how the spacing between the maximum and minimum of the wavefronts is not constant. And the source not only needs to be temporally coherent, but also spatially coherent, which means that parts of the wave in different positions can interfere with each other. And here I'm showing an example of a non-spatially coherent source that has this jagged face. And these requirements actually translate into very specific performance for the light source that we're using. For temporal coherence, we need to use a monochromatic source, which is a source that has a very narrow range of emitted wavelengths. And for spatial coherence, we need to use a very small emission spot illumination. And in traditional lensless holography, the requirement for temporal coherence is achieved by using a laser, and the requirement of spatial coherence is usually achieved by a combination of using a pinhole, so basically a spatial filter that makes the equivalent aperture smaller, and the typical pinhole sizes are on the order of 10 micrometers. And this is usually not enough per se to ensure high enough spatial coherence, so that's tied with a large Z2, a large sample to imager distance, which helps also with spatial coherence. So while lensless microscopy overcomes the limit of the field of view versus resolution limit, and also it's much simpler, it's still expensive because it uses a laser, a pinhole, and those need to be aligned to each other. It's also still bulky because it requires a large source to sample distance. So what we set up to explore is, okay, can we simplify these systems? And to do that, we actually leverage CMOS light sources. And the use of integrated CMOS light sources brings about three main advantages. The first one is that since we are exploiting the high fabrication resolution of CMOS, we can generate very small emission spots, which eliminate the need for a pinhole, and therefore just ensure spatial coherence without the need of that pinhole. We can also realize illumination arrays by exploiting the scalability of CMOS. Again, we can fabricate or replicate structures very close to each other with very high repeatability, and that allows us to realize arrays that can be used to improve the SNR or do subpixel shift imaging. And we can also, the fact that we're using CMOS makes that we can integrate the camera and the source on the stage. So we can go from a traditional lensless holographic system that looks like this, that uses 2 chips, moving parts if you want to do shift imaging, and it's relatively bulky in the sense that it requires a long sample to source distance, to a much simpler system that looks something like this, where you have a single CMOS chip that contains the illumination array and the camera. There's no mechanically moving parts because the equivalent of moving the sample can be achieved by turning on different sources on the LED array. And it's compact because since this source is very highly spatially coherent, it doesn't require long distances between the source ends. And in order for us to do that, we basically need 3 things. The first one is to actually fabricate and demonstrate a CMOS array of these sources. The second one is to adapt our lensless holographic configuration to the fact that the chip and the source are on the same plane. And the third one is to adapt the reconstruction process to the particularities of our source. So that's what I did in this section, and that's what I'm going to talk about next. And first, I'm going to start by the realization of subwavelength spots with subwavelength spacing LEDs. And again, the first thing we need is to achieve a small emission spot, and we can achieve that by localizing the place where the carriers are injected. And that's a concept that was mainly developed by Dr. Jin Xue and Dr. Zhang Li during their PhD thesis. And the idea is relatively simple. So we have a polysilicon slab that's on top of a p-doped crystalline silicon, and those are separated by a very thin gate oxide. And when we apply a bias, a filament, a very small, very thin silicon filament is formed between the 2 of them, which electrically contacts both of them. And so now, when we apply a bias, actually electrons are injected into the crystalline silicon through the filament, and they, as soon as they get in, they radiatively recombine with the holes that are accumulated, and that generates photons. You can see here how we can achieve this very, very high localization by only allowing the electrons to get into the crystalline silicon through that very thin filament. And the other thing that we need is to achieve a very close spacing between these emitters. And what I did for that is just provide different polysilicon access region so that we can achieve distinct filaments and therefore distinct emission spots. And the minimum distance between these access regions is basically set by the rules of the CMOS process that we're using. And in our case, we get a vertical spacing of about 180 nanometers and a horizontal spacing of about 600 nanometers. Okay, and we actually fabricated this device, and we did that in a fully commercial microelectronic CMOS process. It's GlobalFoundries 55 BCDL, which is again a commercial process that's used to making devices on your phone, especially like power amplifiers for your phone. And it's well established. It has shipped more than 3 billion wafers over time, so it's a very established process. And here's a basic stack of a polyCMOS process where you use the polysilicon to make the gate of the transistor. Your crystalline silicon is the body, and then you have source and drain implants for NMP implants for your source and drain. And what we basically did is just reuse these exact same layers to realize our LED as I showed. And that's great because now we can again exploit the advantages of CMOS, where we get very high scalability. We get all these big wafers, like 12-inch wafers, but and we can dice it and get many chips. And that's actually an actual picture of the chip that contains the LED array amongst other components. So we took one of these chips and experimentally characterized it. And the first thing we did was measure the spectrum. We get a center wavelength of about 1130 nanometers, which we expect because that's close to the bandgap of silicon. And the spectral bandwidth is about 120 nanometers. And that's actually a problem for holography because, again, as I said, we need high temporal coherence, and 120 nanometer bandwidth doesn't allow for that. And we'll see how we address that later with computational algorithms. We also measure the power emitted by these sources, and there's actually 4 lines here, although we can't really see them. Each line is for one of the LEDs, which then shows again the scalability of CMOS and the repeatability of CMOS because you're getting very similar sources. And the power at about 200 microns is 50 picowatts. Now, if you're used to LEDs, that's actually not a lot of power, but you have to remember we're using silicon, and silicon is not an efficient light emitter because it's an indirect band material. And well, that's the price you have to pay. It's thanks to the fact that we're using CMOS that we can achieve this very, very small emission spacing. And that's what I'm showing here, where we basically just took a picture of the emission of the array by turning two of the LEDs on. And I'm showing here 1 and 3, so the vertical, the horizontal line, and then the vertical one. And we can basically get the emission spot size and the emission spot spacing by simply fitting two Gaussians to a line profile. And with this, we got about a 700 nanometer emissions. And that's great because that ensures high spatial coherence without a pinhole. If you remember, before I said that typical lens holographic microscopes use a 10 micron diameter hole, we're using a 700 nanometer, so that's about 10 times a smaller emission spot, which means that we can achieve the same degree of spatial coherence with 10 times lower total source to sample distance. So that's where we get all this miniaturization. And the spot spacing that we achieved was between 445 nanometers in the vertical direction and 680 nanometers in the horizontal. And this result by itself is already pretty significant. This is the first time that a sub-wavelength spot, sub-wavelength spacing LED array has been made in silicon or in CMOS in any silicon-based process. Not only this, but we can actually compare the performance of our array to the performance of other arrays of nanometers. And there's actually only two in the literature. Both of them were made on gallium nitride. And if you look at the pitch that we achieved divided by the wavelength, and that's an important metric for imaging and coherent imaging in particular, we actually achieved the smallest pitch shown. Compared to gallium nitride, though, we get significantly lower emitted powers, about 1,000 times lower. And that's expected because we're using an indirect band material. Nevertheless, the fact that we're using CMOS, again, brings about many advantages. And the most important one here is scalability. So if you look at the pictures of the arrays, it's really, really hard to see how they can grow, right? Like the metals are there. There's no really real way to wrap more metals inside there in both cases. And that's because gallium nitride only has one metal layer. Instead, typical CMOS processes have anywhere from 3 to 8 metal layers, so it's actually very easy for us to contact them. And another important detail is that we have a transparent top contact, right? Our polysilicon that we're using as a top contact is transparent to the light that's emitted. And that makes it very easy to contact without having to worry about occluding part of the light that gets emitted by this. And that's actually not true in gallium nitride because they don't have such a. Okay, so now we have our LED array that can be integrated with a camera. Now we need a way to redo our lens holographic system so we can redirect the light from the source back into the camera. And we can do that using a mirror, pretty simple, and in a configuration that looks like this. And this results in two main particularities. The first one is that there are two holograms of the same sample formed at the image. One corresponds to the path that first bounces off of the mirror and then interacts with the sample, and the other one first goes through the sample and then bounces off of the mirror. And these two holograms will have a different magnification because they travel different paths after interacting with the sample. And because there's two images formed on this image plane, there's a little bit of a field of view limitation because we need to make sure that these two images don't overlap each other. And if that happens, we won't be able to recover correct data, at least easily. And there's been some work on using mirrors for reflection holography before, but they require the use of a beam splitter to redirect the light to the places that you want it to, and they still use two distinct chips, one for the source and one for the camera. All right, so we actually experimentally demonstrated this, and so I took one of the chips, or unfortunately, we didn't have a chip that actually had both the LED array and the camera on the same chip because we're not a group that makes cameras. So what I did is take one of our chips with the CMOS LED and mount it on top of a commercial CMOS imager, then put it in a configuration with a mirror and take a picture, and it actually works. You can see here a picture taken with one LED on, and these are 20 micron beats, and you can clearly see the two samples with different magnification. And this is great, it works, but we actually have 4 sources in our array. Can we do something with that? And the answer is yes. One of the things we can do is improve the SNR of our imaging system. And for us to do that, we first need to take pictures of the same sample with different LEDs turned on. So we first take one with LED 1, LED 2, LED 3, LED 4, etc. Then we need to extract the shift in between these images. And it's important to notice that there will be a shift between the images taken by these devices just by virtue of the spots being differently localized. And we can do that by using a cross-correlation algorithm, computational algorithm. And once we have this subpixel shift sampling, we can actually fuse the 4 images to make one image that has a low SMR. I'm showing here, this is the picture of a hologram with 1 LED turned on, and that's the picture with 4 LEDs fused. It's hard to see any difference. We can magnify it a little bit, and you'll see how maybe if you focus on the area where there's actually no beats, you can see how the speckle is lower in that picture compared to this one. We can actually compute the peak signal to noise ratio. We get about 5 dB increase in signal. And yeah, the fact that we're getting subpixel shift is actually great, and it can be used for other applications. The most exciting one is the use of super resolution through a technique that's called subpixel shift sampling. But in order for that to happen, you need to take more than 4 images. Usually around 20 images or more are required for that to work, and we don't have 20 subpixel shifted images because we only have 4 LED arrays. All right, and the last part was to adapt the reconstruction algorithm to our source. And for that, we actually used an untrained physically informed neural network in a framework that's called deep image prior. And the basic idea is to recover an object F from an experimental measurement G, where we know the relationship between those two is a matrix H. And with this, basically, we just have to basically feed a neural network with random noise. And this neural network generates an estimate for the object that we want to recover. Then we use the matrix H to estimate the observable, and then we compare it with the actual measurement that we took. We can do that using mean square or other metrics. And we basically just backpropagate through the weights of the neural network to iteratively get a better estimate of the object. And in the case of holography, the object that we want to recover is an image sample. Our measurement is the hologram, and the matrix H is the matrix that describes the propagation of the light from the sample plate to the image plate. And that's a well-known matrix. All right, and this framework works well, but we actually need to adapt it to our particular source. And the main characteristic of our source is that it's broadband. So what we did for that is actually adapt this matrix H to account for multiple wavelength. And it was mainly developed by Dr. Iksun Khan in Professor George Field Studies group. And we actually showed how it works pretty well, right? So here's a picture of reconstruction that doesn't account for multiple wavelength, and here's a reconstruction that accounts for multiple wavelength, and you can see how the resolution and the contrast improve a lot. And in order for that to happen, to work like this, the scenarios or the pictures need to have relatively high SNR. That's not the case in our pictures because we're using silicon, and the silicon is not a very efficient idea. So to overcome that limitation, I actually added a step where we add additive white Gaussian noise to the generation of the estimated observable, and that noise is different every time. And that prevents the neural network from overfitting into the noise that's present on the image hologram. This actually works pretty well. So here's a picture of the acquired hologram. Again, these are 20 micron beats. And this is the actual sample that we went to recover, taken with a bulky, expensive microscope. Here's a picture of a traditional reconstruction, no neural network, no broadbandness, anything. You can see how there's a little bit of matching, but the contrast is really bad, the resolution is really bad. Here's a picture using the deep image prior reconstruction without noise addition, and it's actually worse than the traditional reconstruction. And that's again because it's overfitting to the noise in the hologram. And here's a picture of the reconstruction with the noise addition, and you can see how there's a really nice matching between the two. And if you don't believe it, and actually fuse up the two of them, and it's actually very nice monster. And this brings me to the conclusion of this first section, where I've shown how we can overcome the limitations of traditional lensless microscopes that are bulky and expensive by a combination of using CMOS LED arrays with very small emission spot and the use of a deep image prior algorithm to overcome the high temporal coherence, the low temporal coherence of objects. This is actually, as far as I know, the first ever microscope that has only a single chip for illumination and the camera. And on the way, we've also shown the first sub-wavelength spacing, sub-wavelength emission spot silicon LED, and also a novel reflection holographic configuration that doesn't use it today. And while most of my talk have been on, or most of the pictures I've shown have been on beats, we can actually reconstruct other biologically relevant samples. That's a honeybee wing, and that's a housefly. All right, so with this, I'm gonna shift gears now and talk about my work on the analysis of non-uniform OBA architectures for optical beamforming applications. And as I said, that's more focusing on the use of CMOS photonics for processing the illumination before being emitted. And an optical phased array is a coherent optical phased array is a system where you have closely spaced emitters, and you can control the phase at which the relative phase at which they are emitted by. And by changing that relative phase, we can actually achieve beam steering. And here in this plot, I'm just showing as I shift the relative phase between these 7 antennas, we can actually achieve beam steering. And if we freeze that at a given angle, we can plot what's known as the radiation pattern. And this radiation pattern basically just shows the power emitted at each angle in polar coordinates. And from this, we can get all the performance specifications of an OPA. First thing to realize is that there is a main lobe where the power that contains the power that's emitted in the direction that we want, which is at 0 degrees in this case. But there's usually also side lobes, which are other lobes that have the exact same power as the main lobe, and that are emitted at angles that we, in principle, don't want the OPA to emit. And that results in a limitation of the field of view, which is basically just the spacing, the angular spacing between the main lobe and the closest side lobe. Another important figure of merit is the side lobe suppression ratio, which is basically the difference between the power emitted into the direction that we want and any other power emitted within the field of view. We also care about angular resolution, which basically is the beam width of the main lobe and the optical power contained in the main lobe. So a high performance OPA wants a large field of view, a large angular resolution, a high side lobe suppression ratio, and a high power contained in the main lobe. And we can now look at a generic OPA architecture or integrated OPA architecture, and basically looks like this. So you have a light source that's usually external to the chip, and that just generates the light, and then it gets coupled into the chip. Once it's in the chip, the first thing it goes through is a polar distribution network, whose goal is to divide the light into different parts so that they can be fed to each of the emitting antennas. And before going into the antenna, they go through a phase shifter, which is an element that sets the relative phase at which we want to emit the light for each of the emitters. After the phase shifter, it just goes into an emitter that basically redirects the light from propagating in plane to out of plane into free space. And as I said, we want a large field of view, and in general, that means that we need to achieve antenna spacing that's close to the half wavelength. And that's actually very challenging because as the spacing decreases, there's crosstalk concerns of very close antennas. It also requires the miniaturization of both the routing and the phase shifter, because in general, they need to fit in between the space of the antennas. Not only this, but we also want a large angular resolution, and that is basically related to the total length of the OPA. And if we want to have very, very small spacing between antennas for a large total length, that means that we need a very large number of antennas. And actually for reasonable applications, we need on the order of 10,000 antennas a month. And that's a concern, because if we need 10,000 antennas, then we need 10,000 phase shifters, because in general, we require one phase shifter per antenna. And if we look at typical phase shifters used in OPAs, there's basically two. One is a thermal phase shifter, which basically just uses a heater to heat the waveguide and change the properties of the light. That's a very simple phase shifter, so that's usually the one that's used in experimental demonstrations of OPAs. It has a high power dissipation on the order of a milliwatt or more, and it requires length on the order of 500 microns. Another alternative is to use depletion type PN junction phase shifters that achieve the modulation of the light properties by changing the carrier concentration in the waveguide. And those have a very low power dissipation, but since the phase shift effect is weaker, require usually longer length on the other millimeter. And by looking at this table, it should be obvious that having 10,000 phase shifters is complicated. One, the power consumption increases a lot. If we have 10,000 elements with a milliwatt each, that's a total of 10 watts being dissipated on a tiny chip. If we have 10,000 phase shifters with a millimeter each, that's 10 meters of waveguide that need to fit on the chip, and also the control gets more complicated as we are adding more and more. And this concern is actually real. If we look at the literature on demonstrated OPAs, there's actually none that can achieve the required performance for typical applications. And in my work, I consider two main applications. One is LiDAR. You might be familiar with it. It's basically the extension of radar to optical frequencies. and FSO or free space optical communications, where you basically have two OPAs that talk to each other through free space. And in this plot here, in the shaded areas are the areas where we want to be to have enough performance for either LiDAR or FSO. And you can see how none of the published literature have that required performance on their worst axis. And this is maybe a detail, but most of the OPAs have two steering axes, and I chose the worst one just because that's one that limits the. And not only this, but also like only two OPA demonstrations to date have more than 3,000 elements, whereas real world applications, as I said, require 10,000. So that's actually a problem, right? And it's natural to ask, well, are there alternative architectures we can use to improve this? And before being able to answer that, we need a way to compare different OPA architectures. And for me to do that, what I did is try to come up with a figure of merit that illustrates what an OPA wants to do in the end. And that's basically maximize SNR while minimizing power consumption. That yields a very simple figure of merit, which is just the SNR divided by the power consumption. And for SNR, I consider that the SNR is proportional to the square root of the immediate optical power, and that just means that I'm considering the propagation of a collimated beam into free space. So with this, we can go back to the simple integrated OPA architecture, and first we need to identify the two main sources of electrical power consumption in an OPA, which are mainly two. One is the power required to operate the laser, and the other one is the power required to operate the phase shifters that control each antenna. And for the immediate optical power, we need to account for all the optical losses within the chip, and also the fact that not all the power is emitted into the main lobe. So it's also a big thing. Okay, and so with this figure of merit in mind, what I wanted to explore on this section is the use of non-uniform OPAs and see if non-uniform OPAs can actually help. And almost 90% of the experimental demonstrations on OPAs now are based on uniform OPAs, which are basically just you have a set number of elements and the spacing between these elements is constant. You can also use a non-uniform OPA where you use a set number of elements, but the spacing between them is not the same. And by looking at this, the first advantage of non-uniform OPAs should be visible, which is the fact that these two OPAs have the same length. Therefore, they have the same angular resolution, but the non-uniform OPA has less elements, which means that it has less power consumption because it has less phase shift. We can also plot the radiation pattern of each of the antennas, sum all them up. We can see how in a uniform OPA, we see the main lobe, which is at an angle where there's constructive interference between all of the phase grounds emitted by each antenna, but there's also side lobes where there's also full constructive interference of all these antennas at angles that we don't want. In a non-uniform OPA, we still have that main lobe, but we actually don't have any side lobe. And that's just by virtue of having non-uniform spacing that makes it so that there's no full constructive interference between all of the antennas at any other angle. And that's great because it basically ensures a 180 degree field of view without requiring a halfway line spacing, which eases a lot of the requirements of spacing or of size on the phase shifter and the rod. Nevertheless, if we look at the density of the lines emitted on the main lobe, you can see how there's less density on non-uniform OPAs compared to uniform OPAs. And that basically means that there's less power emitted into the main lobe. That's actually a well-known thing in radio frequency phased arrays. It's called the thin derivatives, and it basically says that if we have we have an uniform array with 50% of the elements compared to a uniform array, it will have 50% of the power emitted into the main. And while that's a well-known result in radio frequency, it's actually rarely discussed in the literature on non-uniform OPAs. And I think that's pretty important, so I just want to mention it here. The other thing, or the other limitation of non-uniform OPAs, it's actually because they have non-uniform spacing, it's hard to ensure that there's no partially constructive interference at other angles, which basically means that there's a lower side lobe suppression ratio compared to uniform OPAs. And actually, I studied that, and here I'm plotting the side lobe suppression ratio of different architectures for non-uniform OPAs, and that just means different approaches to place the antennas on the non-uniform OPA, because since we have non-uniform spacing, we have a lot of ways of placing the antennas. And the dashed line on top is the side lobe suppression ratio for a uniform OPA, and we can see how indeed non-uniform OPAs cannot achieve as high a side lobe suppression ratio as desired, or as uniform OPAs, right? But this plot here also shows that if we want to achieve the highest possible silo sufficient ratio, we need to use what's known as non-redundant OPAs, which basically just try to ensure that no two antennas have the same spacing. No two antennas in the array have the same spacing. That's actually a well-known mathematical problem. In 1D, the solutions are known as Coulomb rulers, and in 2D, they are known as Costas arrays. And this is great because now we know that if we want to use a non-uniform OPA, we should use either a Coulomb ruler or a Costas array to ensure the maximum silo sufficient. Okay, and now we're at a point where we can go back to our figure of merit. And by looking at this, it's actually not obvious if non-uniform OPAs help or not, because they have a lower emitted power because of the thin array curves, but also a lower power consumption because they use less elements. And so it's natural to ask, well, does it actually ever make sense to use a non-uniform OPA? And to explore that, what I did is plot the ratio of the figure of merit for a non-uniform OPA to the figure of merit of a uniform OPA. As long as this number is larger than 1, so this green shaded area here, using a non-uniform OPA will be better. And you can see how actually what decides if we are on the green area or the white area is this value A. And A, it just corresponds to the ratio of the phase shifter electrical power to the laser electrical power. As long as this number is larger than 4, using non-uniform OPAs will be better. Just to reinforce this, if the phase shifter electrical power is 4/5 of more than your total electrical power budget, it's better to use a non-uniform. And we can translate that to actual numbers. And if we use thermal phase shifters or injection-based phase shifters, we have about 1 milliwatt of power dissipation. Using non-uniform OPAs is better for as little as 1,000 elements per day. If instead we use phase shifters, PN depletion phase shifters, then we basically need 1 million elements, which is basically never going to happen. So this means that non-uniform OPAs are good for relatively large power consumption phase shifters. All right, so this brings me to the conclusion of this section where I've systematically studied the performance trade-offs of non-uniform OPAs, which is something I've actually never seen done in the literature. I defined a figure of merit to compare different OPA architectures, and I've identified scenarios where the use of non-uniform OPAs can help ease the requirements on phase shifter area and spacing. Area and power consumption. And that's great because it basically gives you an architecture recipe. If you know the number of elements that you need to achieve your field of view and angular resolution, and you know the phase shifter you're going to use, you know if you want to use a uniform OPA or a non-uniform. And while most of my work, all I've talked about on the OPA section is a theoretical study, I've actually, for the past year, I've been working for Google X in actually making these devices a reality. So yeah, we're basically doing it for free space optical communications applications. We have two terminals that talk to each other. And most of my work has been on the design of the photonic components that go into the OPA chip, including ring resonator-based compact and low power phase shifters, and also a high rejection filter for enabling full duplex full duplex communication on OPAs. Also done some system level work, including the use of round OPAs for improving the link bands and these OPAs. Great, and with this, I'm now going to conclude my talk, where I basically argued how the advent of large-scale integrated photonics has a lot of potential for imaging, and in particular, the realization of large arrays of sub-wavelength spacing, sub-wavelength emission spot arrays. And I want you to realize that this was the main content on both sections. The imaging, it was to achieve this subpixel shift spacing, and on the arrays, on the OPAs, it was just to achieve large field of view. And throughout my thesis, not only on the stuff I've talked about, but also other things that I contain in my thesis, I've actually presented novel sources, architectures, and applications to help. And in terms of future work, on the section of lenssless holography, I think there needs to be some work on improving the immediate optical power by these sources. I believe there's enough growing space to make that higher and then get a larger SNR. I also think we need to show an actual array with a large number of emitters. I actually have a design on my thesis, but we never fabricated it, so it'd be great to fabricate it and show a super resolution with it. And I also think there's a lot of potential to use computational algorithms to improve the reconstruction quality, not only on the DB match prior, but also on the fact that there's two images of the same sample. right now we are not really using that, and I think there's something there that we can use. And in non-uniform OPAs, I think the main focus has to be on designing more compact and more efficient phase shifters. Oh, sorry. But I also think that it'd be interesting to explore architectures that need less phase shifters than emitters, and that's in theory possible, but in practice very hard to achieve because of application variations in your CMOS chip. And I actually think that device trimming, post-fabrication device trimming is a very important topic for integrated photonics, the world of integrated photonics in general, if we want to scale to a really large number of emitters. So I think device trimming is actually really good research path for the future. And yeah, so during this time, I've talked separately about the integration of the light source and the detection and the integration of the illumination processing. And it's natural to ask, well, can we actually do both on the same CMOS photonic chip, right? Can we generate the light, process it, and detect it on the same chip? And the question is, can we actually realize waveguide coupled LEDs in CMOS? And it's actually not that big of a leap, because in the first section, I showed you how we can achieve surface emitting LEDs in silicon. And then we can ask ourselves, well, can we, instead of emitting it into free space, can we capture it on a waveguide and then let it propagate? And the answer is actually yes, and that's chapter 3 of my thesis. And in short, we basically just took regular optical waveguide, or a common optical waveguide, a rig waveguide in this case. We had a PN junction, and that makes it so that radiative recombination happens mostly at the junction of this PN junction, which lines very well with the optical mode, which means that we achieve a relatively high coupling efficiency to that mode. And we actually shown experimentally characterize these devices, and we can actually achieve light emission after propagation. So the light is generated here, then it propagates through waveguides and gets emitted into free space through gradient coupler. And that's great because it actually opens up the possibility of doing imaging applications with previous on-chip processing before being emitted into free space. And not only this, but actually the light can also be detected on chip by using integrated photodetectors. And that opens up a whole new range of applications, including sensing, processing, optoisolators, etc. Now, chapter 4 of my thesis is on using these exact same architecture for sensing, for realizing refractive index-based biases. Okay, and I just want to go back to this and just say that the end goal of my thesis, I guess, is to enable the transformation of currently expensive, specialized, bulky imaging systems to the consumer market by the help of miniaturization and lower cost, brought about by integrated photonics. And you guys might be familiar with Moore's law, that basically states that the number of transistors fitting into a chip doubles every about 2 years. I actually think integrated photonics has its own Moore's law. We're back a lot back on the years, but I actually believe that we're at the start of the corner of the exponential increase. And I think as the number of elements inside a photonic chip explodes, the applications of integrated photonics will also explode. And with my thesis, I hope this thesis serves as a little stepping stone towards exploiting these large systems for imaging applications. All right, and with this, I just want to thank my PI, Professor Rajiv Ram, for all his guidance. As he said, I've known Rajiv for quite a while now. I joined as an undergrad student, and ever since, it's been great to have his guidance, not only on academic, but also professionally. He's always been there. I really appreciate your approach to research and also to mentorship. I think that's been great. I also want to thank my committee, Professor Jelena Taras and Professor George Papastalis, for the help on making this a reality. And I also want to thank Dr. Amira Tabaki, who was my mentor when I first joined the group. He basically taught me everything I know about the characterization of photonic components and a great deal about the design of these. I also want to thank Professor Christine Payne, who gave me the opportunity to do research at Georgia Tech at a point where I wasn't sure if I wanted to do research, and thanks to that, I actually decided to do a PhD. So basically, thanks to her, or partly thanks to her, is why I'm here today. And I also want to thank the whole physical optics and electronics group for their shared experience, the wins, the losses, the banter, everything, especially Gavin and Neely, who've always help me out when I needed it. Also acknowledge funding sources like ASHA, IARPA, NASA, Google X, and Smart. And finally, I want to thank all of you guys. This has been a pretty wild ride. It's been tough at times, it's been great at times. It's been a lot of work. And if I'm here, it's partly thanks to you guys. So thanks a lot. I want to say thank you also to the people on Zoom, my family who supported me over this whole process, even when it meant being away for a really long time. And all my friends in Spain, in Boston, in California. Thanks a lot, guys. This has been a great ride, and I hope you enjoy it. Thank you.
At this point, we basically take questions from the audience. Any questions? Anyone? Questions from Zoom? Hi, Mark. That was really cool. I have a question about the first part of the talk where you talk about the CMOS photonics part. Currently, with the device that you have, can you like image light? As in, like, can you like have things at any time, or do you have to like push sources for too long?
So there are holographic systems that do live shoot, like video. Right now with our device, I don't think we could do it because since the power is so low, we need to integrate, we need to take pictures integrating for quite a long time. So I don't think it'd be enough for video rate.
A long time.
Oh yeah, like it's between 5 and 10 seconds. So it's a relatively long time. If we could, one, get better cameras. So one thing I haven't talked about is that we're using silicon to detect the light emitted by silicon, and that's actually not great in terms of responsivity. The silicon cameras are not super sensitive to the light emitted by itself. But there's ways to make better responsivity out of CMOS, and I think if we use a camera like that, we could get larger signal and therefore get closer to that type of rates.
Thank you. Really awesome talk. Just really fascinating the fact that, just my question is, silicon film is actually doing the image. What is the process that's actually setting the wavelength that it's emitting at? If you're kind of on the edge of the band gap, like where is that coming into play?
Well, I guess, so it's basically just interband communication, right? So that's the emission. But there's actually, it's a little bit more of detail, like the spectrum is relatively broad, and that's because it's very high energy carriers that make the spectrum broaden as you increase the bias.
Thank you.
I was curious for this, mentioned you had a device that had many pixels for doing this sort of subdiffraction imaging. I was curious, like, is it just a question, do you add more pixels and then you're done, or is it more involved than that?
To achieve super resolution?
Super resolution, yeah.
No, basically, if you only have 4 images and you're trying to get a 2x resolution, that's a very loose problem in terms of variables. So if you look at the literature, it'll take anywhere from 20 to 100 to achieve a 2x resolution. So basically, there's too many free parameters for you to get a good estimate.
And then do you need like a 2D array or something, or is it?
You do need a 2D array. Well, you need a 2D array if you want to achieve 2D super resolution, right? Okay.
Yeah. Thank you for the great talk. Just, nothing like directly linked to the material you presented, but you mentioned like device streaming.
Device streaming,
yeah, as mechanism to pull it from start of the manufacturing process has ended. Just curious, like what ways do you envision, especially in CMOS, to actually do that?
That's a great question. So, I mean, there's some work by IBM on using germanium thin films. So they basically have a waveguide, deposit a very thin layer of germanium, and then apply a bias to like basic. I think it creates some like silicon germanium, something like that, to trim it. I think that's okay, but it's not fully CMOS compatible, which kind of breaks the point. So the thing that I would like to explore would be actually to use polysilicon. you can partly crystallize the polysilicon if you apply a lot of heat to it. And I think that could be used for trimming, but I don't know. I haven't done it. I like to try it. But I mean, using polysilicon for photonics is tricky because it has a high loss in theory, but I think there could be something there that doesn't require the addition of thin films, however.
And one last question. When you measured the emission spot size, is that, like, did you account for the point spread function of, like, a microscope, you took that image with? Are the spots actually smaller than that?
They should be a bit smaller, but
Does it
it's,
matter?
not really. I mean, it matters if you care about intensity of light emitted and things like this,
But
but
that
not
spot
for
doesn't
us.
come into now, like, the reconstruction algorithm anymore. That
It comes into the required space to get enough spatial coherence, right? So what I said, like, if you need 10 microns, you might need, let's say, 10 centimeters. If you have 1 micron, you need 1 centimeter. If you have 500 nanometers, then you need half a centimeter, right? So that's where it would come from, but in terms of performance, it doesn't.
It's basically saying, well, the reconstruction algorithm doesn't have it.
It doesn't.
It doesn't have the PSF as an input.
No.
Okay, all right, thanks, thanks, Mark, again. So at this point, we ask everyone except for the committee to leave, and then the committee will get a chance to ask questions.
Okay, guys, so I'm gonna end the meeting because now I have to leave this night. Thanks everyone for coming and I'll talk to you later. Thank you.